Bismillahirrahmanirrahim. Today we will cover lecture number 20 of Design of Material 2, and in this lecture we will cover theories of elastic failure. There are 5 theories and another one is the sixth one. Introduction. When dealing with the design of structure or component, the physical properties of the constituent material are usually found from the result of laboratory experiment, which have only subjected the materials to the simplest stress condition. The most usual test is the simple tensile test, in which the value of stress at yield or at fracture, whichever occurs first, is easily determined. So actually in this paragraph, it is shown that when you have to design structure or component, in designing, the function of that component might be to bear complex stresses, but we cannot do the complex experiment in the laboratory. So what we do, we do the easy experiment like the simple tensile test, and then we have this theory to relate this simple test with the complex state in such a way that if it is within that limit of theory, then we say for designing purpose we say material is safe, and if it is going out of the given criteria, then we say material is failed. So actually and the benefit of this is we don't have to perform complex stress condition test experiments. So the strength of material under complex stress system are not usually known except in a few particular cases. So in complex system it is very difficult to know the stress exactly. In practice it is these complicated system of stress which are more often encountered, and therefore it is necessary to have some basis for determining allowable working stresses so that failure will not occur. Thus the function of the theories of failure is to predict from the behavior of material in a simple test when elastic failure will occur under any condition of applied stress. So theories are relating simple test with the condition of applied stresses and predict when the failure will occur. A number of theoretical criteria have been proposed, each seeking to obtain adequate correlation between estimated component life and the actually achieved under surface load condition for both brittle and ductile material application. Again, same thing. The 5 main theories are maximum principal stress theory or Rankine theory, maximum shear stress theory or Gust or Tresca theory, maximum principal strain theory, Saint-Venant theory, total strain energy per unit volume, Hay theory, shear strain per unit volume or Maxwell-Hurber or von Mises theory. In each case, the value of selected critical property implied in the title of the theory is determined. Title is show what is the critical property which is we are doing with respect to that property is determined for both the simple tension test and a 3-dimensional complex stress system. These values are then equated to produce the so-called criterion for failure. So when we equate these two, we have criteria of failure listed in the last column of the table. So we go to the table. So these are the 6 theories that we will study today, and this is the criteria. According to this theory, if sigma 1 is the maximum stress, principal stress, and sigma y is yield stress by simple tension test. So when these equate, that is the limit for this. So sigma 1 should be within this limit or equal to this. If it is greater, sigma 1 is greater than sigma y, according to this theory, material design is unsafe. Similarly for maximum shear, this is the criteria, principal strain, this is the criteria, total strain per unit This is the criteria, and this is von Mises. This is most important. This is the criteria, and for Mohr, this is the criteria. In table, sigma y is the stress at the yield point in the simple tension test, and sigma 1, sigma 2, sigma 3 are the three principal stresses in the 3-dimensional complex stress system in order of magnitude. And in Mohr circle and in analytical method, we know how to determine sigma 1, sigma 2 for 2D case, and for 3D, sigma 3 is also the case. Thus, in case of maximum shear stress, so maximum shear stress, that was obviously the difference between these two, sigma 1 minus sigma 3, is the greatest numerical difference between the two principal stresses. Taking into account signs and the fact that one principal stress may be zero, each of the 5 theories listed in table will introduce in detail in the following text, as will a 6th theory, that is Mohr's modified shear stress theory. Whenever the previous theory A to E assume equal material strength in tension and compression, whereas this 6th number theory, Mohr modified theory, attempts to take into account additional strength of brittle material in compression. So according to this theory, compression is more of brittle material as compared to tension. So first theory, maximum principal stress theory. This theory assumes that when the maximum principal stress in the complex stress system reaches the elastic limit, stress in simple tension failure occurs. So the criteria of failure is thus sigma 1 is equal to sigma y. It should be noted, however, that failure could also occur in compression if the least principal stress, so sigma 1, sigma 2, sigma 3, so sigma 3 is numerically least, is least due to sign, were compressive and its value reached the value of yield stress in compression. So if this value is reaching, if this value is reaching the yield stress in compression, then we have to equate this with the criteria sigma y, that is sigma y yield stress for the material concerned up before the value of sigma yt. Sigma yt means yield stress in tensile test, T for tensile test, was reached in tension, and initial criteria is therefore sigma 3 is equal to sigma y compressive. So if sigma 1, sigma 2, sigma 3, if sigma 1 is reaching limit, then we will equate this, and if it is not reaching, it is within safe, but sigma 3 is reaching sigma y in compression, sigma 3 for compression, it is least value, negative value, so it is compressive. So if that is reaching, so that is the criteria. Which criteria is occurring earlier will be the criteria for this maximum principal stress theory. While the theory can be shown to hold fairly well for brittle materials, there is considerable experimental evidence that theory should not be applied for ductile material. For example, even in the case of pure tension test itself, failure for ductile material take place not because of the direct stresses, but in shear on plane at 45 degree to the specimen axis. So we know shear is at angle of 45 with the principal stresses. So for ductile material, not only tensile stress is playing its role, but also the shear. And in pure tension test, ductile material fail due to shear. Also, truly homogeneous material can withstand very high hydrostatic pressure without failing, thus indicating that maximum direct stresses alone do not constitute a valid failure criteria for all loading conditions. So, to show locus, envelope or locus for this theory, we will draw sigma 1, sigma 2, and limit is sigma y for tension as well as for compression. So this is compression, this is for tension. So from here maximum value is here. If so, when you join this, it will be a square. If the value of sigma 1 or sigma 2 are within this square, then material is safe according to this theory. And if it is going out of this square, then material is unsafe according to this theory. So this is the way how we apply theory in designing. Maximum shear stress theory. Now criteria was principal stress, but in second theory criteria will be maximum shear stress theory. So maximum shear stress will be the criteria. This theory states that failure can be assumed to occur So failure will occur when the maximum shear stress in the complex stress system becomes equal to that at the yield point in the simple tensile test. So simple at yield point in the simple tensile test, what is the value of shear stress? So that value of shear stress is the limiting value, and that is obviously half of sigma y in tensile test. So we have to equate this with the maximum shear stress, and maximum shear stress according to, if you know the Mohr circle, that was equal to sigma 1 minus sigma 3 over 2, because this is the diameter and half of this is the radius, and that is shear stress equal to radius. So that is the way to know this, and we have covered this in previous lectures. This is tau max, maximum shear stress, and this is the value of shear stress at in simple tensile test when the yield stress is reached. So yield stress is for tensile test. To relate it with shear, half of yield stress is the criteria. So this is criteria from simple tensile test, and this is from our Mohr circle or our theory, that is the value of tau max, and we have determined in formula in chapter 9 how to determine the maximum shear stress or principal stress. So here shear stress applied, 2 is cancelled, sigma 1 minus sigma 3 is equal to sigma y. That is the criteria for this theory. The value of sigma 3 being algebraically the smallest value, taking account of sign and the fact that one stress may be zero, this produces fairly accurate correlation with experimental result, particularly for ductile material. So this is better for ductile material and is often used for ductile material in machine design. The criterion is also referred to as Triska theory. So it is also called as Triska theory and is one of the widely used laws of plasticity. So that is the locus or envelope for maximum shear stress. So when you draw this is square, then this triangle, square, triangle, so that is the envelope. So if the value of sigma 1, sigma 2 lies within this envelope, it is safe according to this theory. If it is going out, it is unsafe. Maximum principal strain theory. This theory assumes that failure occur when the maximum strain in the complex stress system equals that at the yield point in the tensile test. So according to, actually we are comparing the strains. So strain for simple tensile test is strain at yield point in simple tensile test will be equal to sigma y over E. And what will be the value of epsilon 1? That obviously equal to, if you apply generalized Hooke's law, epsilon 1 will be equal to sigma 1 over E minus mu Poisson ratio into sigma 2 over E minus mu Poisson ratio, sigma 3 over E. So that is epsilon 1, and this is epsilon y, means the normal strain at yield stress from tensile test. So when you E will be cancelled out, so result will be sigma 1 minus mu sigma 2 minus mu sigma 3 is equal to sigma y. That, so this becomes the criteria. This theory is contradicted by the result obtained from the test on flat plate subject to two mutually perpendicular tensions. So when you perform test, the results are contradicted, so it will be not used most often. The Poisson ratio effect of each tension reduces the strain in the perpendicular direction, so that according to this theory, failure should occur at a higher load. This is not always the case. So this predict failure occur at higher load, but it fails before that experimentally. The theory holds reasonably well for cast iron, so it is well for cast iron, but is not generally used in design procedure these days. So if its result on, and this is the locus for this. If it is lie within this rhombus, material is safe, and it is going out, it is not safe. So that is the way. Then maximum total strain energy per unit volume theory, fourth theory. The theory assumes that failure occur when the total strain energy in the complex stress is equal to the to that at the yield point in the tensile test. Total strain energy in complex system and total strain energy at yield point. If both are equal, so that give us the criteria. From the work of criterion of failure is thus. So what will be the total strain energy at yield? That will be sigma y square over 2e. That is the energy, and we know how to get this. And we have to equate this with this 1 over 2 into sigma 1 square plus sigma 2 square plus sigma c3 sigma minus 2 mu into sigma 1 plus sigma 2 plus sigma 2 plus sigma 3 plus sigma 3 plus sigma 1, small bracket close, square bracket close. So when you equate, so this will be the criteria. This theory gives really good result for ductile material, but it is seldom used reference to the theory below, because below theory is more good than this. This is also good, but next theory is more good. So when you draw the envelope, so this will be the envelope like this. So if value is coming inside of this ellipse, then material is safe according to this theory. This is the value of strain energy for 3 decays. So we have weighted those. Then maximum shear strain energy per unit volume or distortion energy theory. The strain energy of a stress component can be divided into volumetric strain energy and shear strain energy component. Total strain energy is volumetric strain plus shear strain. The former being associated this one with volume. Former mean this one volumetric, previous former with volume change. So volumetric strain energy will change the volume and no distortion. The later, this one shear strain energy, produce distortion of the stress element. So this is distortion. This causes the distortion. That's why distortion energy theory it is called. This theory states that failure occurs when the maximum shear strain energy component in the complex stress system is equal to that at the yield point in the tensile test. So again, that is the value for strain energy. And for yield, we will put sigma y. And for 3D system, it will be equal to this. And you equate, criteria will be sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square is equal to sigma y square. And continuing this topic, this theory has receiving considerable verification in practice. So it is and is widely regarded as most reliable basis for design, particularly when dealing with ductile material. So this theory gives more accurate result in practice. That's why we will use this, especially for ductile material. It is often referred to as von Mises or Maxwell criteria. Is probably the best theory of the 5. It is also sometimes referred to as the distortion energy and maximum octahedral shear stress theory. So that is the envelope, failure envelope for maximum shear strain energy per unit volume theory. So that is the envelope. If the value of is coming inside of this, material will be safe, and if it is out of this ellipse, material will be fail. How to draw sigma 1, sigma 2? You have to draw value of both yield stress on this axis, yield stress on this axis, this point, and similarly this. So this will be the major axis, minor axis will be at 45 degree with this sigma 2, or at 90 degree from this. So this is how this ellipse is drawn. Then sixth, that is modified for ductile material normally. Mohr's modified shear stress theory for brittle material or internal friction theory. Brittle material in general show little ability to deform plastically and hence will usually fracture at or very near to the elastic limit. And of the so-called yield criteria introduced above, therefore will normally imply fracture of a brittle material. So brittle material do not show plastically, so fracture will usually fracture or very near to elastic limit. So that is yield criteria. It has been stated previously, however, that brittle material are usually considerably stronger in compression, stronger in compression than in tension, and to allow for the Mohr has proposed a construction based on his stress circle in the application of maximum shear stress theory. In figure A, this is figure A. The circle on diameter OA is that for, so this is, if you see, that is tau is being pure shear is applied. This is pure tension is applied. This is pure compression is applied. For pure tension, this is the circle. O is the circle. For pure compression, this is the circle, and for pure shear, this is the circle, middle one. So O is that for pure tension, the circle on diameter OB that for pure compression, and the circle center O and diameter CD is that for pure shear. Each of these type of test can be performed to failure relatively easily in the laboratory. An envelope to these curves shown dotted then represent the failure envelope according to Mohr theory. A failure condition is then indicated when the stress circle for a particular complex stress condition is found to cut the envelope. So that will be the envelope. So a close approximation to this proposed Mohr suggests that not only the pure tension and pure compression failure circle need be drawn with OA and OB equal to yield or fracture strength of the brittle material. Common tangent to these circles may then be used as the failure envelope as shown in figure B. So close approximation of this is we are drawing just this small and this bigger and just taking the tangent. So this will make the envelope, approximate envelope. Tangent to this envelope then represent the condition of failure at the point of frequency. So that will be the becomes the criteria. Sigma 1 tension yield stress as tension plus sigma 2 yield stress as compression is equal to 1. So combined yield loci for the various failure theories, so that has been drawn combinedly. This is principal stress, maximum shear, this is maximum shear stress, maximum principal strain, total strain, shear strain, modified Mohr. So that is drawn here. So if material is here, it is safe according to every theory. If it is here, it is safe just by this theory, and rest of the theory are says it is unsafe. So that is the value of this combined yield locus. Then in the loss limitation of the failure theory, in most cases von Mises is the best one. In most cases, the von Mises dissolution energy theory is considered to be the most reliable and relevant theory, with the following exceptions. For brittle material, the maximum principal stress or Mohr internal friction theories are most stable. Principal stress, that is theory first or sixth last theory, are suitable for brittle. It must be noted, however, that former is definitely unsafe for ductile material. So these will be the unsafe for ductile material, especially this principal stress. Some authorities also recommend the Mohr theory for extension of the theories to the ductile fracture consideration as opposed to ductile yielding as assumed in the elastic theories. All the theory produce similar result in loading situation where one principal stress is large compared to the another. This can be readily appreciated from the graphical representation if a load line is drawn with a very small positive or negative slope. Here this is load line. The greatest discrepancy between the theories is found in the second and fourth quadrant of the graphical representation, where the principal stresses are of opposite sign but numerical equal. So this is first and fourth. For biaxial stress condition, more modified theory is often preferred, provided that reliable test data are available for tension, compression, and torsion. Because for more we need these three data for these three. In most journal biaxial and triaxial stress condition, the Tresca maximum shear stress theory is the most conservative, the most safest theory, and this together with its easily applied and simple formula probably explain its widespread use in industry. So in this case, it is used widely. The Saint-Vincent and principal strain theory or total strain theory per unit volume are now rarely, if ever, used in general engineering practice. So they are not used first and fourth theory. They are not third and fourth theory. They are not used. Maximum principal strain and total strain energy per unit volume. So mostly we use Tresca or von Mises for ductile material. For brittle, the first maximum principal stress or Mohr internal friction theory we use. Thank you very much.